Okay, hello. Hi, welcome to the channel. Okay, so as for this channel, what I will be looking at, okay, is superposition first. So if you have questions on superposition, you can ask those. Okay, so I have a first question here. So this is from Pranav. Pranav, you are asking, so to go through the relation between phase, path difference, and how to derive each other. Okay, Ken. Now, by the way, the materials that I am going to be referring to, as well as the questions that some of them that I've chosen, if you go to Kai Academy JC Telegram, you can also see a copy. Okay, if you feel you need to refer to the hard copy, then you can actually download it from there. If not, you can just refer to the screen. Okay, now so path difference and phase, how are they related? What we need to know, right, okay, is that for path, it will have units of length because it's actually a measurement of distance, right? Whereas for phase, it's actually units of radian. So one is an angle and then one is actually in distance. So how do we convert, right, the two? Okay, so let me see. Just a quick check. I think my screen, is it showing the correct screen? Okay. Okay, so path difference is distance. Phase, which will be corresponded to something called phase difference, right, is actually an angle. Okay, now so if you're going to find path difference, right, there must be two things, otherwise you won't be finding a difference, two things that you're trying to find. So let me use this question below. Now there are two radio transmitter A and B, they have the same power, separated by a distance of 5 km. Okay, you are given the frequency, okay, that the sources are emitting the signal at, right, and then there is a car. Now this car travels along a line parallel to and 12 km away from the line joining the two transmitters as shown. Okay, now and there's an aerial. So the aerial in the car detects a resultant wave, right? So once we see something like this, we know this is a superposition interference question because there's two sources and then two sources are sending a wave to a point. So two source interference. Okay, at one instant, the car is at position P, right? A distance of 12 km from this transmitter A. Now, you see, the first question then asks us, state and explain the nature of the interference between the two waves that is received at point P. So this is what I call a formation question. That means at this point, is it maxima, minima due to constructive or destructive respectively? Okay, now so let's look at path difference. It's a distance, right? So since it's a distance, I want to see how much distance does the wave travel from A to P and how much distance does it travel from B to P. Okay, I'm going to call the first distance AP, right, and the second distance I'm going to call it BP. Okay, you're going to find the difference between these two, and then I'm going to take a modulus. All right, now so since this is 5 km, this is 12 km. Okay, if you do a Pythagoras theorem in this question, so geometry is very common. So if you do a Pythagoras theorem, you will get 13 kilometers. That's from B to P. Right, so if I would now do a AP minus BP, it's going to be 12 minus 13 modulus. So the path difference, usually we write it with the symbol delta x, right, is equals to this, is equals to 1 meter. Okay, now how to then convert your path difference into phase difference? So in order to do that, now what we need to note, right, is the following relationship. Let me use this blank below. Every time you have got one wavelength, okay, one wavelength will correspond to a phase of 2 pi. Right, remember, phase is an angle, right? So it's corresponding to an angle of 2 pi, okay, which we also know is actually one wavelength. Right, so I want to now find for a particular path difference, delta x, right, what angle will this correspond to? So for example, if delta x is half a wavelength. Right? If it happens to be half a wavelength, then delta x converted to phase difference will become pi. Okay, so if you think it's actually proportion and you want an angle at the end of the day, so phase difference, which we can write with a delta sign since it's a difference. So phase difference is then delta x over lambda times 2 pi. Okay, so in this question, you see I've already found delta x. All right, so this delta x was 1 meter. Now what do I use to find the wavelength? Now Cambridge requires us to remember this for your year 2 level, because in year 2 then we will revise again your entire EM spectrum. So a radio wave is actually a part of your EM spectrum. So radio wave will travel at the speed of light, which is 3 times 10 to the 8. Okay, so you now know its velocity. Alright, so since I know its velocity, then I can find its wavelength given that the frequency is given to us. Okay, so if you were to calculate this wavelength, that will be just take 3 times 10 to the 8 divided by 1.2 10 to the 6. There's a kilohertz here. Okay, so for exam purposes, please be careful with your prefixes. Okay, so then there is a kilo, so this is 1.2 times 10 to the 6. So V over frequency. Now if I am not mistaken, I think this one is 250 meters. Okay. Yeah. Okay, so then I use this formula. So this will give me a delta x of 1 meter. Right, and then lambda is actually 201 km actually. My bad, this is kilometers, so this should be 1. Take me a while. Okay, so this will be 1 km divided by 250 meters, so 0.25, then times 2 pi. Okay, 1 km divided by 250 meters, that's 4, times 2 pi, that will give me 8 pi. Okay, all right, now 8 pi is actually an even multiple of pi. So if it's an even multiple of pi, it actually results in a constructive interference. Okay, so this is actually a qualitative question. How am I going to put this into words? Right, so explain the nature of the interference. Right, so the stating, I will say it is a constructive interference. For the explanation part, then I'll talk about the path difference. Okay, so the path difference is, you can show a bit of math, right? So you can show path difference is 13 minus 12 equals to 1 km. The wavelength is 250 meters, therefore phase difference due to path. Okay, it's 8 pi after you're done your calculation. Okay, and therefore the waves will arrive in phase. Okay, this is an answering technique, right, that you can take note of. So whenever you want to conclude that something is going to be a constructive interference, then the corresponding wave or waves, they must be arriving in phase. Okay, and if it's arriving pi out of phase, then it's going to be a destructive interference. All right. Okay, so since I've started on this question, let me continue with this one. All right, it's going to then extend to the next part, which is on interference pattern. So there's a part 2. Okay, so describe how the resultant amplitude of the 2 radio waves at the car varies with time as it travels at a constant speed along the line shown in the figure below. All right, so this is a 1-mark question. Okay, so a describe question doesn't require you to now give explanation. So it is important to just point out what will be observable, right? Either visually, auditorily, and so on and so forth. So in this case, because these are radio transmitter, right? So and there is a signal detector inside the car, so the signal detector will show us fluctuating maximas and minima. Okay, so it'll be fluctuating back and forth. between maxima and minima. Okay. Reason for that, okay, is because as the car is, if let's say this wasn't a description question, it was like a 2 marks, describe and explain. Okay, then what am I going to be talking about? So as the car is traveling, there will be a change in path difference, right? Because you see now it is 13 minus 12, so there's a 1 km difference. But suppose the car was now in the point that is equidistant from both transmitter, right? So if it is equidistant from both transmitter, over here, path difference will be 0. Right? Path difference of 0 means a phase difference of 0 for sure is constructive interference. Okay, so if you recall, this was previously 8 pi, a phase difference of 8 pi. At the midpoint, this was a phase difference of 0. So in fact, if your examiner wants to test even deeper understanding, they may ask us, to calculate, for example, how many maximas or minima will be detected when it moves from P to the, equidistance position, right? Let's say I call this point Q. Okay, let's say I call this Q. So when it goes, from P to Q, right? How many maximas and minimas will be observed? So at 8 pi, that will be 1 maxima, 7 pi minima, 6 pi maxima. You can actually just count, right? So just count, then all the way until 0. Then in between, you will be able to get all your maximas and minima. Okay, so that's part 2. Okay, now, so part 3 suggests a change that can be made at the transmitters that will prevent interference between the two waves without changing the frequency. Okay, so usually suggest question are questions that your examiner will put at the last part of the question. So these are things that may not be readily inside your, so it forces you, to think at a higher order. Now we need to recall, right? What are the conditions that causes interference to take place? Okay, most of your notes, the first condition that will maybe point out is that the sources must be coherent. Right, so here is you want to prevent interference, so therefore we will use incoherent sources. Okay, now what does incoherent, or for that matter, what does coherent actually mean? Okay, now in the question they told us that you see the two waves emitted are in phase at the transmitter. There is this line over here. Right, the two waves emitted are in phase at the transmitter. So what this means is that when the transmitter at A produces a crest, the transmitter at B also produces a crest. This is in phase. So when we say that these two sources are coherent, what we mean is that this in-phase relationship, right, will be perpetual. Okay, the transmitter A and B will perpetually be in phase. Now, when it is incoherent, what does that mean? That means right now, maybe the two waves that's emitted are in phase. But maybe 1 minute later on, they decide, okay, they're going to be, for some random error in the system, they decide, okay, I'm going to be pi out of phase. And then maybe 1 minute and 10 seconds later, they decide that it's a pi over 2 out of phase. See, so this incoherence, it keeps changing the phase at the source, right, will mean that whatever we calculate, right, 1 minute later it's going to change, 1.5 minutes later it's going to change again, and so on and so forth. So there is really no point to try and work out whether it's constructive or destructive if there is no stability. It keeps changing. Okay, so that's why incoherence will be one possible answer. Okay, another one, right, that is also necessary for interference to take place, that will be polarization. Okay, so but please note, polarization only works for radio or anything that is a transverse wave. Okay, if it's a longitudinal wave like sound, then you cannot suggest this polarization. All right, so for transmitter A and B, if they were polarized in perpendicular direction, okay, so if they were polarized in perpendicular direction, it doesn't work as well. Now, why is that the case? You see, right, if let's say your waves are polarized in the same direction, so you have got now transmitter A and transmitter B. So whenever transmitter A produces a wave that is oscillating vertical direction, oscillating up. Transmitter B, okay, produce one in the vertical direction as well. So this is polarized in the same direction, parallel direction. Okay, so once the wave travels and it arrives at point P, right, the one where the car is supposed to be, then you're going to get two vertical displacement adding up. This is like a vector sum. So when you get two adding up, right, then this one is going to give you 2 times the amplitude. Okay, but if you were to shift to a point where there is a destructive interference, right, at the destructive interference, then what happens is the wave from A will be maybe a vector pointing up. The wave from B will be a trough, so that will be a vector pointing down. The resultant is 0. Right? This is a true destructive interference. You will receive a minima. Okay. Now, if they were polarized in perpendicular direction, now here's what happened. Let me use a different color. Maybe I'll change to blue. So let's say the wave from transmitter B is not vertical, it's horizontal. So there is a wave now, there is this being produced this way. Once the wave from transmitter B reaches point P, okay, so at the constructive interference, let's look at the vector sum. It'll be a vector upwards. You add to a vector horizontal, right? So vector sum tells us, oh, we got to solve the what we call the parallelogram method, tip to tail method. I mean, so the name not critical. As long as if the name helps you to remember, then yes, right? We use the name. So the idea is you must have this nice close geometrical shape. Okay, either a triangle or parallelogram. Now you see at the destructive interference. Alright, so previously is I'll take the vector up, I will turn it into a vector down. Now I have a vector to the right, I will turn it to a vector to the left. You switch one of the vector. But notice what happens here is there is no cancellation. You just get a vector in the 90 degrees direction. So whether it's at so-called the constructive, now there's also no point calling it constructive or destructive because there's no interference. At both points actually there is the same amplitude, the resultant. Okay. So Pranav, I went a bit longer than what your question was. Okay, but I also wanted to show the application of phase and path difference. This is a very good question. It, in fact, should be often the starting point because it gives us an understanding of two-source interference. Okay. All right. Any other question? I tried to address questions that you all have first. If you have no question, then I'll just go through some of the selected question in the this prepared set. Okay. Okay, so I could perhaps now show you guys, let's see where most questions usually are. Single slit diffraction. Okay, single slit diffraction. So this one is something that a lot of students also tends to have problems with. Okay. Now, so this question comes from 2018 Cambridge question, all right? So we are told there is laser light. Now, laser by itself is already coherent. So there is no need to, basically it will be able to undergo constructive, destructive interference, etc. Okay, it's incident normally on a single slit of a particular width. Most school notes should use the symbol B, okay, for this slit width. So that would be 12 micrometer. Okay, the light diffracts and the laser pattern is formed 2.7 meters away. Okay, the screen is parallel to the plane of the single slit. The diffraction pattern is formed on the screen. So part of the diffraction pattern shows the variation with displacement from the center of the pattern of the intensity of the light is shown, okay, in figure 3.2 over the page. Okay. Right. So actually they are trying to draw for us an intensity displacement graph. What actually will be produced on the screen will look something like this. So there is a maybe the laser light, I'm assuming red. So if it's a red laser, on the screen now you will actually see a smeared out light, okay? If I think I have a photo, yeah, something like this. Okay, right, so this is actually the single slit diffraction. Okay, so this point and this point over here, which are called the first minima. All right, so the one in the middle is the central maxima. So there are two first minima, okay, on each side. So this is the central max. Okay, so the first minima, according to the question, right, occurs at about 0.14 meter. Okay, this is from the graph. Now, so if the graph tells us that it is 0.14 meter, okay, then if I were to add this value here, so it'd be something like this. Right. Okay, the formula that you have to memorize, okay, for the single slit diffraction will go something like this. So sine theta first minima, right, it's actually governed by this lambda over b relationship. Right. So if that's the case, now the question asks us for the wavelength of the laser light. So lambda will be equals to b sine theta first minima. Okay. Now b is given in the question. Right, so it's 12 micrometer. So what I currently don't have is actually the angle at the first minima. Okay, so imagine now this is a geometry question. So there's a lot of geometry, that you can expect in superposition. So very worthwhile to be very adept at your trigonometry, small angle approximation, and so on. Okay, so let's say this one, right? So this will be the angle theta. So notice tangent theta is opposite over adjacent, right? So tangent theta is 0.14 over 2.7 meter. Make sure your units are consistent. Right, so then that gives us a theta. Okay, once you have do the inverse function solve for your theta, then what we can now use is this. So I will sub this theta here, right? So that's the next step, okay, in order to work out the wavelength. Okay, now see, the single slit in B is now replaced by a narrower slit. So on figure 3.2, sketch the new diffraction. Oh, sorry, you can't see the thing so well. Okay. So the single slit in B is now replaced by a narrower slit. So on figure 3.2, sketch the new diffraction pattern. Okay, now so the formula, right, tells us that if this B, right, the slit width were to decrease, okay? So once this decreases, then actually the angle at which the first minima occur will increase. So essentially, what that means is that, let me use green color now, the angle to the first minima must increase. Right. Assuming it's the same slit width which allows the same amount of light to go through, then from a conservation of energy point of view, now that your energy is being spread out, right, over a larger angle, the maximum intensity should drop. Okay, so you might have a graph, no extra values are given to us, right? So I wouldn't know how high exactly or how much you will spread by and so on. Make sure it's a bit hard for me to draw freehand. You try your best in the exam to draw it symmetrically. Okay. Right. Okay, so that's the answer. Okay, D part 1. All right, state and explain the changes to the observed diffraction pattern in figure 3.2 when visible light of a longer wavelength is used. Okay, so when visible light of a longer wavelength, this is the, okay, so right, when visible light of a longer wavelength is used, same thing. So this is a change of variable that again you can use the formula, right, to help you to explain. Okay, so with your wavelength increasing, right, then your theta will also increase as well. Okay, most students again have no problem if this one's a standard change of variable question. Okay, so the one from experience that most students have problem with is D part 2. All right, so in D part 2, when white light is incident, okay, on a single slit, the central fringe is colored at the edge and has a white central region. Explain this observation. All right, so the formula basically is telling us that the larger the wavelength, the larger the angle that it is going to split by. Okay, you guys don't know this yet, but again in year 2, okay, in a topic called quantum, right, it becomes very useful for you to actually remember the wavelength of the visible spectrum. So red color has a wavelength of approximately 700 nanometers. Okay, whereas violet has about 400 nanometers in wavelength. These are just approximation. It's not that exact because it's always a range. Okay, now according to the formula then, right, sine theta first minima equals to lambda over b. Now you can now see this relationship being played out. The red light having a larger wavelength, its first minima will be at a larger angle, right? And violet, smaller wavelength, smaller angle, so on and so forth. So your Roy G. Biff will now spread itself out. You notice the red will be on the outside, violet will be on the inside. Okay, and because all the different wavelengths will coincide right at the central maxima, right, then there will still be a central white region. Right, so all wavelength maxima at the hence the central maxima is white. Okay, use a larger font so you can see better. Right. Whereas for the other wavelength, so their minimas will be different, right? So all other wavelength first minima at different angles. If you want to show off a bit, not necessary, but if you want to, it helps, okay? Gives your examiner a better impression, right? With red at a higher wavelength, violet at a smaller, wavelength, you can add that in, right? But the question specifically doesn't require that, like I said, right? A good impression doesn't hurt. Okay, so have their first minima at different angles, and therefore the central fringe will be colored at the edge, okay? The spectra or spread, right, of colors. Spectra is a term that you will also learn in year 2. Okay, so this is the single slit diffraction effect. Okay, in 2018, Cambridge only tested, it's kind of like a solo question, right? One single effect. Okay. Now, if your school teacher wants to use superposition, right, as the question that generates the bell curve. So what they can potentially do is, combine the single slit diffraction with the Young's double slit effect. So two kind of concepts gets blended together. Okay, let me show you an example of that. Okay, so this is the 2021. Paper 3, right? So in paper 3, it's actually very common for concepts to be combined, not just within the topic, sometimes across topic as well. So here we have a double slit consists of 2 parallel slits, each of width. I like to annotate, okay, it's a good practice to label the terms that's already given to you, each of width 0.1 millimeter. Now separation of the slit, so then typically the symbol that school use is this one. It's quite consistent with what Cambridge wants students to use as well. The only one that I know likes to be a bit special and is Hwa Chong. You always have different symbols that they use for superposition. Now, so parallel light of wavelength 590 is incident normally on the double slit. So a screen is placed parallel to the plane of the double slit at a distance of 2.6 meter from the slit as illustrated in figure 5.2. Alright, so initially one of the two slits is covered. Then be like, isn't that going a long about way, right? You just tell us that, okay, actually we thought it's a double slit, now it's a single slit question. Alright, so okay, so one of them is covered. This is a single slit question. Calculate the width of the central fringe of the single slit diffraction pattern seen on the screen. Okay, so the method of calculating this will be similar to our previous question. You use the formula sine theta equals to lambda b to find the first minima. Okay. All right. So then once I've already worked that out. Okay, then what we are calculating next is the width itself. Okay, so here a common mistake that students make, right? Okay, is forgetting that you will only be finding using geometry half of the width. Okay, because the angle theta is only on one side. Right, so once you have found the theta minimum is on one side, using trigonometry, so this is 2.6 meters, you then work out this part, okay, which is half of the width. Okay, so once you have done that, then tangent theta is actually half of the width over adjacent, which is 2.6. Okay, right, and so then from there, finding the width is arithmetic. Right, so we now have a total width of 0.0307 meters. So that's from here to here. Okay. Right, see, so part 2, both slits are now uncovered. Okay, estimate the number of fringes resulting from double slit interference that are seen within the central maxima produced by the single slit diffraction. Right, so this is where the combination comes. So you have a single slit diffraction, you are now trying to apply the double slit within it. Now the technical name for this is then the single slit envelope. Let me explain what this means. Okay, so you see, right, now the theory part, before I show you the working for this particular question. If you have a single slit and then you, let's say, know the width of the single slit, right, you can then use this to calculate now the single slit envelope. Right, so it becomes something like this. So we've seen this question just now. Okay, but imagine the following. So whenever you have got a double slit, and then let's say this is the screen. Okay, so then I have now one single slit. The wave travel outwards, right, and then it produces for us what we know to be a diffraction pattern. Okay, you now have a second wave. I'm going to use a different color, but actually the light is the same. This is from the same laser, because laser is coherent, right? So if I send out a second wave, okay, see, so the second wave, right, must overlap the first wave as well, and it produces its own single slit. Right? Once we do that, right, you see the resultant wave due to constructive or destructive interference. So this evening that was the first concept that we're looking at, whether when two waves travel to a particular point, they arrive, in phase or arrive pi out of phase, giving us constructive or destructive interference. Now, what we know is this: when waves are arriving constructively, you must take their respective amplitude and then you sum it up, right? So if I were to, sum up the amplitude at the center, so let's say this is the new central maxima. Okay, so at the new central maxima, I will be summing up the amplitude from the, let's say the left slit, right, which is around, I'll use the blue color, it's around this point. And then when I sum it up from the right slit, the red one, it's about the same amplitude. In fact, that's the highest, right? So let's call that A. So your resultant amplitude now is going to be 2A. which means your net intensity, right? And this one, very important to remember, intensity is proportional to A squared. So when your amplitude double, your intensity will actually quadruple. So it's actually 4i. Okay, what you will see now is this. So if one slit, I zoom in a bit so it's easier for you to, see the effect that I'm talking about here. Okay. So this is like done in the lab, and then the photo was taken. You see, so if you have one single slit, this will be the relative intensity. But once you have two slits and you find the central maxima, is actually an intensity that is 4 times larger. Okay, the central maxima is 4 times larger. But more importantly now is what happens as we start going outwards from the central maxima. So as we start going outwards from the central maxima, notice this, okay? So let's say now the second, or what we call this, the central maxima. So let's say the first maxima, right, away from the central maxima, right, occurs somewhere here. I'm going to use the green color down to denote. So what you will find is that due to the red color wave, it's a bit lower than the central maxima. Due to the blue color wave, is also a bit lower than the central maxima. You are now summing up two waves that has amplitude smaller than the central maxima, and this is due to the single slit diffraction. Okay, two waves that has a smaller maxima, which means, let's say one of them, it's about 0.8, the other one also about 0.8, example lah. So then your new net amplitude away from the central maxima is now 1.6, right? Which means the net intensity, it's going to be 1.6 squared of I. So I need a calculator to calculate. Okay, which will give us 2.6 intensity, right? So it now creates a drop. So the next one, so let's say the central one is actually 4i. The next maxima will be a smaller value. In my calculation, I'm just using random values, it's about 2.6. So it keeps dropping. Okay, it keeps dropping. So if we calculate, right, to a particular point, which is the minima of the single slit diffraction, right? So once we are at the minima of the single slit diffraction, right, there's nothing there. No matter how we sum up the amplitude, if individual slit sends to a particular point its own minima, there is nothing for you to add. Right? So you notice at the first minima of the single slit, the Young's double slit pattern has no fringe. Okay, so that's the underlying theory behind this kind of question. Okay, so once we understand the underlying theory already, then we can apply the math, right, okay, to show examiner that understanding, right? So which one you calculate first? Normally I would calculate the single slit width, but we already did that just now. That was quite a while ago, because I was talking about the conceptual understanding. Okay, but we already calculated the width. Otherwise, this would be my first step. Okay. Now, in the Young's double slit, there is a formula that you must memorize, because the fringes will be regularly spaced out, and because they are regularly spaced out, the fringe separation X is given by lambda d over A. Okay. So where lambda is the wavelength, d is the distance, 2.6. Okay, and then A is the slit separation. So all these are given in the question, so I'll substitute it here. Now, so once I have substituted the X values in, and I also know what is the width of the single slit, right? So if you record this pattern over here, what we will do is something like this. I'm going to find the distance of half the width. Next, which we have already done, I'm going to find the distance between two maximas of the double slit pattern, which we have also found. Right? And then now geometrically, I'll just divide the two. So I'll take half width, divide by x. Why do I do that? The moment I do that, right, I will then know which maxima is the one that falls at the minima location. All right. So in this particular diagram, it happens to be the third one. So there's a central maxima. This is the first, second, and the third. So the third maxima landed at the minima of the single slit. Okay, you'll be very careful also when you're explaining, right? Because there's maxima, minimas, and these terms, they just sound like each other. Okay, so in this particular diagram is that. Okay, so for this particular case, when we do a calculation, so if I take half of the width, divide by the fringe separation, you will get 14. That means the 14th. Okay, you must remember carefully, the 14th maxima is the one that will not appear. Right, so if the 14th one doesn't appear, that means the 13th one will appear, and there is one which is right in the middle. You can call it the 0th one. Right, so there's one in the middle, 13 on each side. Okay, so the total number of fringes is 27. Right, so the math actually is not very hard. Cambridge gave students 3 marks actually because they wanted students to think through the concept, and apply. Okay. All right, so that's for the Young's double slit and the single slit diffraction. So if you are online, I hope that helps. At the moment, is there anything that you all want to check with me? At the top right of the screen, you should also see a WhatsApp number. If you have question that you want to show via screenshot, you can actually send it to the WhatsApp, or you can use the YouTube chat function. Okay. Okay, at the moment don't have, right? So what I will perhaps then share also is this concept called Rayleigh's criterion, right? I also get students asking me about this one a lot. Okay, so for the Rayleigh's criterion, right? The basic idea behind Rayleigh's criterion is we now know that due to the single slit diffraction, any light that passes through a slit, right, will always spread a little bit. Okay, imagine now you have 2 lights that is passing through a slit. Those 2 lights, right, will each produce their single slit diffraction effect. So let me try and draw that out. Say this is the screen. No, the screen is here. Okay, so alright, so let's say this is the screen. Okay, you have got a slit. And then you have got now 2 light source. I'm going to call these 2 light source S1 and S2. So I have got now this S1, and then I have another one that is S2. Okay. So I have to kind of separate them a little bit. Once S2 sends a wave through the single slit, I use a dotted blue line, right? So then we know that when this wave eventually hits the screen, right, what results is actually a single slit diffraction pattern. Okay, so that it looks something like this. So that's from the blue source. Actually, it's the same color. Again, I'm just using 2 different colors, so it's easier for us to visualize. Okay, in reality, it's the same color. It could be the grayish white light that you see in the diagram. Now, the other light source, let's say the blue light, right, also sends now its own wave through the slit, and then it will also land on the screen, and then you will now see another single slit pattern. Okay, now without any formula, right, think of it this way. If these 2 sources are very far apart, that means this angular separation, right, the angle between the 2 sides is called the angular separation. Okay, so if the angle between them is very large, then the 2 single slit diffraction that you see on the screen will also be very well separated. We call that well resolved. Okay, now on the other hand, right, we can try and imagine the following. Suppose now I bring S1 and S2 closer and closer and closer and closer together. Okay, so when S1 and S2 now gets closer and closer together, right, so let's say S1 is now here, S2 is just a short distance away from it, so it's here. Right, so if I now trace out the light that travels from S1 and the light that travels from S2, by the time they hit the screen, you see their respective single slit diffraction pattern will be so closely overlapped that I cannot tell that it's actually from two different sources. This looks like it was just from one source. Right? So you will then say this is not resolved. Okay, now there is a, I feel there is a real world application of this that we can probably relate to, you know. So when you are at the traffic light or pedestrian crossing, right, and then you're waiting for the green man to flash. Okay, now if you are looking at the, you know, the light, right, the traffic light, close up, you will actually see that it is made out of tiny LEDs, right? Either it's green or it's blue, but it's actually made out of individual tiny LEDs, right? When you go further and further away, at some point, right, our eyes lose the ability, right, to distinguish these different light source from each other. Agree? Right, so at some point it becomes unresolved. We just see one whole patch or one whole blotch of you know, green or red, whichever color it is. Why is that so? Right, so the reason is because if you imagine, right, these two sources S1 and S2, right, retains their separation, so it keeps this distance. Okay, but then I bring S1 and S2 further and further away. Okay, away from the slit. The slit actually is our eye, because our eye has the pupil that allows light to go in. So once S1 and S2 goes further and further away, this angle theta due to geometry will become smaller and smaller. Okay, so where exactly does Rayleigh's criterion comes in? You see, so in physics, we are often interested in finding the turning point. Right, so where exactly is the turning point, right, such that it is what we call just resolved. Okay, that point where it is just resolved is sort of like the critical turning point. Any angle slightly smaller, you cannot resolve it anymore. Any angle slightly larger, okay, you know, you can actually tell that it's two separate light sources. Right, so the point where it is just resolved according to Rayleigh's criterion, right, is the point where the separation between the two obeys this formula. So at this angle theta, it is just resolved. So I'll just write theta r. Okay, so that's actually the practical understanding that we will need. Then you see what the question actually gives you, right? Okay, to help you to solve the question. So space shuttle orbits at a height of 330 km above the Earth. It carries two panels separated by a distance of 24 meters. And the panel reflects light of wavelength 500 nanometers towards an observer on the Earth's surface. Right? The observer views the panels with a telescope that has an aperture diameter of 85 millimeters, so that's B. Right? Assuming that the panel acts as a point source of light, which of the following is correct? Okay, so to know whether it's resolved or not, I need to later check with the Rayleigh's criterion. Can I find the angular separation as measured from the aperture? Yes. So the way to do that is a bit of geometry. So I'll just draw it here. There is two panels. All right. So let's say this is the Earth. This is the observer. Okay, so what we do, right, okay, is I'm going to draw one line over here, one line over here. I want to find this angle. Apologies for the ugly line. All right, so then the separation between the two, this is 24. Okay, what I'm going to do here now is a geometrical trick. I know that the height is 330 kilometers. Look at the numbers, okay? This separation is 24, away from the Earth, 330 km. Right, so because this distance is so large, this angle theta is going to be a small angle. If it is not a small angle, then what we will do is actually similar to the single slit diffraction method. I find the central width. Okay, but because it is a small angle, right, you can do this approximation. So in circular measure, when we study radian, right, the angle radian is actually the arc length over the radius, S over R. imagine now theta becoming very small. So once your theta becomes really, really small, the arc length, which we denote with S, right, actually becomes, you can't really tell that it's an arc anymore. It's actually just a straight line, right? This part over here is just a straight line, okay? And then this will be your angle theta. So the fastest way to calculate your angular separation is simply just taking the so-called arc length, divide by, again, so-called radius. So in this question, arc length is here, so this is S. Okay, the radius is actually this distance, which is approximately 330 km, right? So which is why theta now is 24 divided by 330,000, and that gives you 7.3 times 10 to the minus 5 radian. Okay, now Rayleigh's criterion gives us important angle. So then when we take the wavelength divide, okay, by the aperture diameter of 85 mm, all right, so then that gives us 5.910 to the minus 6 radian. Okay, 5.910 to the minus 6 radian is the critical turning point. Any angle smaller than this, it will no longer be resolved. All right, and because the actual angular separation is greater than the angle given by Rayleigh's criterion, conclusion is that it will be resolved. Okay, so answer is B. Okay, anything else, any question that you'd like me to go through? For those of you who just came in as well, so I just went through superposition, because if you have questions from superposition, it doesn't have to be from superposition as well. Some of you have got your promos this week, so if you got any questions from your year 1 topic that you want to check with me, feel free to ask as well. Don't have so far. Let's see if I've gone through the questions that I've prepared. Okay. So the starting part of superposition actually deals with this thing called stationary wave. So in essence, there are 4 phenomena. There's single slit diffraction, there is 2 source, or one of them is the Young's double slit. Okay, and then there is diffraction grating and stationary wave. So all these are actually applications of the principle of superposition. Stationary wave has got the kind of good thing is that there's the least number of formulas that you need to remember, but it has got a lot of diagrams that you need to draw. Okay. Right, so this is the last year actually. So last year's MCQ question. So a tube of fixed length can be used in an instrument such as a bugle to produce sounds of different frequencies. Okay, musician will produce a note at one end and an empty note at the opposite end of the tube with varying numbers of notes along the tube. Right, what is a possible series of frequencies for such an instrument? Okay. So stationary wave in a closed pipe, that's what examiner is actually testing here. How do we know that? There is a node at one end, antinode at the other end. Okay, we have to distinguish between a closed pipe. A closed pipe now, as the name suggests, right, there's one end that is now closed, so that's the node. Air cannot freely move at that end. Okay, the open end will be the antinode. And these are what we call boundary conditions. Okay, the boundary conditions must be satisfied for there to be a stationary wave. In contrast, there is something called an open pipe. So an open pipe, it's open at both ends. So this one is antinode, the other side is antinode as well. Okay, doesn't make sense to close both ends. Once you close both ends already, the sound cannot travel at all, right? So no sound will be produced. Okay, so close end, node at one end, antinode. Now, when they say a series of frequencies, there's also testing now something called the harmonics. And so if we have antinode fixed at one end, node at the other end, the first harmonic, what we call the simplest mode of vibration, looks like this. Right. And because in a stationary wave, right, the kind of easy way to remember the relationship, okay, is this. The distance from a node to a node is always half a wavelength. Node to node, always half a wavelength. So if we now have a node to antinode, right, node to antinode, that must be 1/4 of a wavelength. So if I tell you this is the length of the pipe, the length of the pipe is now resonating at 1/4 of the wavelength of sound. Okay, so if you want to know then what is the frequency that this sound is being produced at, right? Because the aim actually is to produce frequency, but high pitch or is it a low pitch? Right? So typically we write this as F1. Right, the first mode or the first harmonic. Okay, so then that would be V over wavelength, right? But if you rearrange this one, wavelength is 4L, so then this one is V over 4L. Okay, second mode of vibration, you must still maintain the boundary condition. So I use a different color. The length of the pipe hasn't changed yet. So this is A, this is AND. All right, so you add one more node, one more antinode inside. Yep, so that's what it now looks like. You see, just now I was saying that node to node, half a wavelength. The pattern that is now repeating, right, is actually this part. There is a node to an antinode. So I know this one is 1/4 of a wavelength. Inside there is a node to node, that's half. So which means total, this L is actually 3/4 of a wavelength. Right, so when it's 3/4 of a wavelength, then it's actually a different wavelength now if you compare with the first one. This is actually a larger wavelength. The wavelength just got smaller. It got kind of squashed, right? So I will label this as lambda 2. This is lambda 1, okay? Okay, and so if you now work out the frequency of this new mode of vibration, remember wavelength just got smaller, right? So it looks like it got kind of like squashed. So then the frequency must have increased, okay? And so if I do now V over lambda 2, right, so then lambda 2 is actually 4 over 3L and so on. So then when you now divide, you are going to get 3V 4L. Okay, so now if you compare frequency, the second frequency now with the first frequency, it is actually 3 times of the fundamental. Right, it's 3 times of the fundamental. Now if you repeat this pattern, okay, then say you draw another one. Once you draw the third one, actually, the pattern becomes kind of like, you can kind of work it out already. So this is going to be node, antinode, node, antinode, node, antinode. Actually, each time round, the trick is you just add one more loop, which is half a wavelength. So one more loop. So just now there was actually one loop and 1/4 of a wavelength, right? So it's 1/4 plus one loop. Right, then after that you add another loop. Now this total is going to give us, then if you count, 5 over 4 lambda. Okay, so the pattern is it goes from 1/4 to 3/4 to 5/4. Right, if I extend, that means the next pattern is going to be 7/4. The following one will be 9/4, and so on. So we find this pattern, and if you were to calculate the frequency, same trick. So it's V over lambda 3. Okay, and if you solve for the math of that, it's going to give you 5 times the frequency. Okay, so this relationship in terms of the harmonics comes about because of the changing relationship between your L and your lambda. All right, I now know I need to look for a pattern which goes in terms of odd multiple. So it's like one time of frequency, 3 times of frequency, 5 times of frequency. Right, so you look at the options, then this is answer C. Right, so 50, 150, 250, 350. 1 time of frequency, 3 times, 5 times, and then 7 times of the fundamental frequency. Okay. All right, I also do one that is for a string as well. Okay, this string question is the 2017 MCQ question. Now, in this particular year, Cambridge wanted to test students one important factor that they have not tested in maybe 30 years. Okay, so it was a very new concept. It stunned a lot of students. We always assume that the velocity of the wave, right, is fixed when we are solving stationary wave question. You notice in the question that I was doing just now, last year's question, I basically just assume, oh, the V is always the same, right? And actually, we kind of know that because velocity of, the speed of sound in air is about 340 meters per second, right? But the key thing is this: speed of a wave in any medium depends on the medium. So if the speed of sound in air, right, is going to be 340, in liquid it will change, in solid it will change to another value as well, right? So in string it's the same thing. The speed of the wave on the stretched string changes according to the medium. In this case, it is proportional to the square root of the tension of the string. Okay, so this is the key understanding that we must first have, when we solve this question. Velocity can change. Cambridge just seldom change it. Okay, now so velocity is proportional to the square root of tension. String is held under tension between a clamp and a pulley 90 cm apart by a mass. Sorry, Sam. Sorry, I can't see it below and on the right. It's cut off a little. Just let me. Okay. Thanks for the feedback, Sam. Okay, hope it's better now. Okay, let me continue. Now, so the string is held under tension between a clamp and a pulley, 90 cm apart by a mass of 400 grams hanging from the end of the string. Okay, so in this question, then what we need to note is tension wouldn't really appear. The question is going to be changing the tension by changing the mass. So over here, tension is used to support the mass of the string. Oh, sorry, the mass of this block over here. Right, tension in the string is used to support the weight of this mass. Okay, in our pulley question, okay, then the tension is actually constant throughout the string as long as the string is actually sort of massless. Okay, so I can then rewrite now this velocity formula to V equals to K square root mg. Okay, so when the frequency of the mechanical oscillator close to the clamp end is 15 Hertz, the stationary wave shown is set up. This is what we call the fundamental mode of vibration. Okay, there's only one loop. Okay, the hanging mass m and frequency are varied until another stationary wave is formed. So what's the combination that will give us a stationary wave still? Right, so if you recall from the previous question, the thing that is important is boundary condition. Now, in a stretched string, okay, the boundary conditions is that the ends must always be nodes. So if I have to draw the most basic mode of vibration on a stationary wave on a string, it looks like this. Right, the second mode, both ends must still be nodes. You add one more node in the middle, so it goes like this. And so on and so forth. So the third mode of vibration, you have now node, right, and it goes this way. Okay, there's actually a kind of simple formula that we can use now to remember this relationship. So in my mind, what I do is I remember this set of diagrams. Right, so the first mode of vibration is actually one loop. Second mode of vibration is 2 loops. Third mode of vibration is 3 loops. Right, which means the 101 mode of vibration will be 101 loops. Every loop is actually half a wavelength because it's between node and node. right? So if that's the case, then I can basically generalize it like this. The length of the string must have an integer multiple of loops, which is half a wavelength. Okay, so this is the key relationship that governs the pattern on a stretch string. Okay, how does this help us, right? The question, okay, is asking which combination now gives us a stationary wave. Now, for a stationary wave to be formed, n must be an integer. N must be an integer. So if there is a combination of frequency and mass that does not give us an integer value of n, a stationary wave will not be formed. Right, that's the idea. Okay, so I will now make n the subject of the formula. So n, then you get 2L over lambda. Okay, so I need to clear the screen a little bit. Okay, so this is the general relationship. I want to now check for whether n is an integer value or not. Okay, but I need to be able to solve a little bit more variables because this is L, this is wavelength. What we know so far is this, so frequency. Okay, the first piece of information that we know is that when n equals to 1, this is the first mode of vibration. The length of the string was 90 cm. Right, so that was 0.90. Okay, wavelength is velocity over frequency, so it's k square root, and then your mass is actually 400 grams, so 0.4 times 9.81, and then you divide by the frequency of 15. Okay, now so once that's done, what am I trying to solve here? Because all numbers actually have been filled in, the only unknown is the value of k. Alright, so once you have found k, you can actually do a bit of trial and error in this case. There is no shortcut, unfortunately, because there's no way to look at all these numbers, right? And then just because you will have to sub one by one. Right, so once I know the value of k already, right, you can use back the same formula again. So n equals to 2. The length of the string is fixed. You have already found k. Okay, you have to try for the different values of m here, and times 9.81. Right, and then divide by the frequency, which is also variable. So there are two variables here. Okay, so try the different values of m, different values of f, until you find the option that gives you an integer value. If your examiner is less kind, oh sorry, that thing you cannot see on the screen. So if your examiner is less kind, then it might be the last option, which in this particular year is indeed the case. So students who have tried A, B, C, and if you trust that the working is correct, then the answer must be D. If not, then you have to solve for the last one. Okay. All right, for the superposition part, these are the questions that I have prepared. I think it gives us a broad exposure of the different concepts within superposition. Not sure if Pranav, Sam, you guys are still there as well, and some of you online. You got anything else that you want to check? Let me know. Okay, could I explain how to find the width of the central bright fringe for the single slit? Okay, no problem, no problem. Okay, so I'll just use a fresh. Okay, if I want to find the width of the central bright fringe for a single slit, first I need to know what is the wavelength that is coming in. Right, I need to know what is the slit width, and how big the opening of the slit is, as well as the distance, right, of the screen, okay, from the slit. So I need these three values. So once this is given, when the wave travels, you'll get a central maxima here. Okay, the wave will undergo diffraction, so its first minima will be at the dotted line. Right, and what you see on the screen is this, what we call the central bright fringe. Okay, right, so I want to find the width of this. Okay, so I'll just tell myself there's a formula in the syllabus, right, for finding this angle, the angle of the first minima. Right, so then you have already lambda and b. So sub these values in, solve for the angle theta. Now once you have found the angle theta, okay, observe there is a triangle here that I can perform geometry. Right, so this is actually half the width. Okay, so this is actually half the width. Now see tangent theta, right, is actually opposite over adjacent, so it's half of the width divided by capital D. Okay, that's why lambda, b, and d must be given. So then you sub all these values in to calculate for the width of the central. All right, thanks for the question. Hope that helps, Eugene. Okay, so if at the moment no burning question, then if all the best for your promos, those of you who are having it this week. All right, do remember, very common mistake, especially now that you all have done G field. Your examiner likes to give G field graphs, potential against distance, field strength against distance. Sometimes you have, maybe rocket. Sometimes it's Earth and satellite. Sometimes it's Earth and moon, right? All those. One of the key things, because besides superposition, the other one where students usually have difficulty in is G field. Numbers there tends to be very big, and sometimes you have to be very careful with the prefixes that they use on the graph. Right, so on the vertical axis, on the horizontal axis, distance often will be in kilometers. Sometimes the potential will be with a megajoule per kg and so on. Okay. All right, don't just focus solely on calculation question. Well, that's important, right? So if you must make sure you've memorized the correct formula in superposition corresponding to each of the different phenomena. Sometimes I see students, they remember the formula, but you use the wrong formula in the wrong context. It's a bit wasted also, right? So what is good is that if, let's say you like to take your own notes and all that, so write down each of the formulas for superposition, but next to it, draw a diagram to show what all the, like a bit like this one, so Eugene's question, So if I write sine theta equals to lambda b, then what I probably want to in my own summarized note is the diagram where, I remind myself, okay, where does the theta appear? How does that help me to find some of the other quantities and so on? All right, so once you've done that step, okay, of all the formulas and where they specifically get applied, it is very important, right, to then master the explanation question. Okay, these days for physics, that's often where the differentiating factor, is going to arise. Whether we can explain, like for example, just now we're talking about constructive, destructive interference, and then the other kind of explanation question will be the change of variable, like when the wavelength change, when the state wave change, then explain what happens. Sometimes they may ask you to draw, but more often than not, they will ask you to explain. Okay. Right, so then I think that's all for today. Hope it was useful for you folks. And yep, all the best.